All right, Chemistry 3111. This is where we left off last class, was discussing reductive amination, and I told you this is a very powerful reaction, reductive amination, because we can take a ketone or an aldehyde, and we can make primary, secondary, and tertiary amines, starting with ammonia, a primary amine, or a secondary amine, respectively. Now, besides the amine, we also need a catalytic amount of acid, and this new reagent, which is sodium cyanoborohydride. So what I said is that if you take a ketone or aldehyde and treat it with sodium borohydride, well, that will simply reduce the ketone or aldehyde. However, sodium cyanoborohydride will not reduce an aldehyde or a ketone, but it can reduce an imine. And what happens when you take a ketone or aldehyde and you treat it with something like ammonia and a catalytic amount of acid, you produce an imine. So you have that sodium cyanoborohydride in the reaction flask, and as soon as the iminium is formed, or the imine is formed, it's reduced by the sodium cyanoborohydride. We call that in situ, or in place, or in the same reaction flask. So a very powerful way to make amines, very simple, or straightforward, I should say. And if you've ever looked at the structures of marketed drugs, of prescription drugs, you'll see that amines are practically in, or almost ubiquitous. You know, they're in so many drugs that it's very important that an organic chemist know how to synthesize amines. Well, last class we did question 22.14b, and today we're going to look at C. Now remember, when you do reductive amination, it's a way to make a carbon-nitrogen bond. And there are two carbon-nitrogen bonds in this molecule. We have this one here, and we have this one here. Now, depending on which one of these bonds we break, our starting material is going to be different. However, since both of these bonds are incorporated into a ring, it means that our ketone or aldehyde, our carbonyl, and our amine are going to be in the same molecule. So let's imagine we broke just a red bond, right? What would it look like then? If you count the number of atoms, we have 1, 2, 3, or number of carbons, 4, 5, 6, and then the seventh atom would be the nitrogen. So let's draw that out. It would look something like this: 1, 2, 3, 4, 5, 6, 7. The seventh atom would be the nitrogen. Since we have a secondary amine, it means that we need to start with a primary amine, and we would have a carbonyl at carbon number 2. And so this would be our starting material if we were to break the red bond or do our retrosynthesis, saying this is the bond that we want to form, this one right here. And so what we would have to do is to take this compound, and we would treat that with sodium cyanoborohydride, so NaBH3CN, and a catalytic amount of acid. Now keep in mind, we don't have to write anything else in there because, again, both the amine and the carbonyl are present in the same molecule. So if we just mix that all up, it's going to cyclize to give you this compound, our product. So I'm just going to write the word product here like that. Alternatively, we could go and make this molecule by breaking the blue bond, or breaking where I have that blue squiggle, if you will. Well, what would that look like in that case? If I was to break, oh, actually, I actually did the one with the blue bond, didn't I? Oops, Mr. Dion made a little boo-boo here. So what I did, I mean, I didn't make a mistake. This is correct. But this is the one I did. I actually broke this bond, and that's this starting material to make the molecule this way. Sorry, if we break the blue bond, so now I'm switching them here. If we were to break this bond, then you'd have to start with something that looks like this. So we'd have 1, 2, 3, 4, 5, 6, like this. We would have our primary amine here, and then we would have our carbonyl over here. So you'd have the aldehyde there. All right, so this is what we would start with if we broke that blue bond. And again, it would be the exact same conditions: sodium cyanoborohydride, cyanoborohydride, and a catalytic amount of acid. and that is going to give us our product. Again, same rationale. We have a primary amine and we have a carbonyl. This time it's an aldehyde, and that would cyclize this way to give you the exact same compound as if you were to cyclize this molecule. The exact same thing. So there we go. Reductive amination. Give me a thumbs up if you follow me on that. Sorry, I kind of broke the wrong bond, or I was thinking about a different bond when I was writing it. Is everybody with me on that one? Is anybody with me on that one? All right, cool. Let's just take a quick look at D. We have time. There's a couple of ways that you could make D, right? You could break this bond. Let me write a squiggle here. You could break that bond here. Then you've got a really big ring is what you'd have to have. So if you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you were to break that bond, you'd have something that looks like this. You'd have 1, and then we'd have our secondary amine like this. So there, you'd have something like this, and you'd have the carbonyl here. So that's if you were to break that bond, the one that I have highlighted in red. And again, you would treat that with sodium cyanoborohydride, same old conditions, catalytic amount of acid. That's going to give you the product. However, if you were to break one of the bonds in the ring, like let's say you broke this bond here, okay, what would it look like then? Well, then you would have the nitrogen incorporated into a 6-membered ring like this. Okay, so you'd have the secondary amine. Then you have, count them, 1, 2, 3, 4 carbons coming off. So let's write that 1, 2, 3, 4, and then you'd have your aldehyde over here like that. So again, the exact same conditions. Sodium cyanoborohydride, I bet you won't forget that now. And then a catalytic amount of acid. There you go. And that would give us our product. There you go. So a little bit of reductive amination practice. Let's take a look at one more question that deals with reductive amination. This is always a classic in organic chemistry. Methamphetamine, which is crystal meth, is used in some formulations for the treatment of ADD and can be prepared by reductive amination using phenylacetone and methylamine. Well, I know that you all know how to draw methylamine by now. Methylamine is a methyl group that's in a primary amine like that. So that's methylamine. If you're wondering about phenylacetone, I think that everybody here could tell you, tell me what the structure of acetone is. It's just this. It's propanone. That's acetone. So if you just put a phenyl on it, if you just add a phenyl on it like that, that is phenylacetone. So now that we have phenylacetone and methylamine, it says if you do a reductive amination, you'll make methamphetamine. So let's figure this out. We're going to start with our phenylacetone, which is a ketone. It looks just like this. And then we're going to combine that with our methylamine. So this is a primary amine. Therefore, methamphetamine must be a secondary amine. We're going to use sodium cyanoborohydride and a catalytic amount of acid. And what's that going to give us? Let's see. We're going to draw the phenylacetone carbon skeleton. Now, we're not going to have a double bond here. We're only going to have a single bond to our nitrogen with our methyl group on it, right? We're going from a primary amine to a secondary amine, which is what's going to happen when we do a reductive amination. And this is the structure of methamphetamine. So there you go. Now you know how to make methamphetamine. Now, please don't do it. All right. That's enough about that. Okay. Is everybody with me on the methamphetamine synthesis, or at least you follow me on that? Sean, anybody? All right. So now you know what methamphetamine looks like. However, there's something that I'm leaving out here, and that is methamphetamine, the compound that people use to get the high, is only one of the stereoisomers, because you can see that there is a stereocenter in the molecule. I'll let you figure that out on your own. All right, let's move ahead and talk about a little summary of kind of where we're at. Okay, we covered quite a few things in the last class, and we talked about several ways to make a primary amine. Let's just review. We went over the Gabriel synthesis, which is where you start with phthalimide and then you treat it with potassium hydroxide to make this compound, potassium phthalimide, which is a reagent that's capable of doing an SN2 on a primary alkyl halide like this here, and then you treat it with hydrazine to make a primary amine. So that's a really great way to make a primary amine. We also said that you could use sodium azide. So sodium azide is NaN3, right? Na plus and N3 minus. Anyhow, here's the Lewis structure of the azide ion, and we talked about that last class, and we said that once you make the azide, which can react with a primary or methyl alkyl halide to do an SN2 or even a secondary, you end up making the azide, and then you can reduce that either using just regular old hydrogenation conditions will work, or you can use a lithium aluminum hydride reduction followed by treatment with water. That works too. So we covered that. And then, of course, what we just discussed, which was reductive amination, a very powerful, quick way to make amines. Then, so this is just dealing with primary amines. And then we said, well, if you want to make a secondary or tertiary amine, is to use reductive amination. So you take your primary amine, no matter how you get it, and if you want to make a secondary amine, the best way to do that is to use reductive amination. You can take that and perform a second reductive amination and make a tertiary amine. And then if you treat that with some kind of alkyl halide, you can do another alkylation, or do an alkylation, I should say, to make a quaternary ammonium ion or a quat. Anyhow, and we're going to talk about quaternary ammonium ions a little bit more today because we're going to discuss Hofmann elimination to some degree. So let's move on from there and let's see how you could make each of these amines. And there's more than one way to make these, and this is kind of in the same vein as some of what we've looked at today. So I don't want to spend too much time on this question, but let's just say, let's just imagine you wanted to make this compound here. Now, you can make this by reductive amination, is a great way to do this. And you could either do it by breaking this bond here, or you could do it by breaking this bond here. Either one's going to work. Now, if you break the bond in red, then you would start out with an aldehyde, which would look like this. So you'd start it with this aldehyde, and then you'd combine it with methylamine. So methylamine, then a catalytic amount of acid, then sodium cyanoborohydride. There we go. And that's going to give you the product, the desired product. Alternatively, if you were to break the blue bond, then you would start with this primary amine. So 1, 2, there we go. And then you would treat that with acetaldehyde. So a 2-carbon aldehyde, that's called acetaldehyde. We went over aldehyde nomenclature earlier on in the class. Sodium cyanoborohydride. There we go, and that's going to give you the product. So my question to you is, and you can either unmute your mic and answer this, or you could type it in the chat. In B, we have a primary amine. Could anybody tell me what the source of nitrogen would have to be in a reductive amination to make this compound? Where would I get the nitrogen from, since I'm making a primary amine? And it's not a trick question. It's something we looked at just a few slides ago. Can anybody answer that? Where would you get the nitrogen to make a primary amine?
From potassium phthalimide?
So that's, you could, but this one is a secondary amine. Or it's a primary amine, but you have a carbon here that's attached to 2 other carbons. Where's my blue pen? Right, like this. So you have a carbon here and a carbon here. So that would mean that you would have to take potassium phthalimide, right, like this. There we go, like this. And then your alkyl halide would have to be this, okay, a secondary alkyl halide, which would give you some SN2, but it's mostly going to give you either elimination, or it's not going to work very well since this is secondary. If you did a reductive amination, then you're going to get a much higher yield. So what my question is, basically what I'm getting at is, if you go back here, we were talking about making a primary amine using reductive amination, okay, you always get the nitrogen from ammonia. So that's where it would come from. And so if we go back here, what you would want to do is for B, you would want to start with cyclopentanone. So you start with cyclopentanone like this, and then you treat it with ammonia and a catalytic amount of acid. And you would treat that with sodium cyanoborohydride, so NaBH3CN. And that would give you the product. All right, that's enough about synthesis strategies. We're going to come back and try some more synthesis problems today, that's for sure. So let's move on and we'll come back in a little bit. Let me show you a couple more things about amine chemistry that we need to know coming out of organic chemistry too. Do you remember we talked about this in the carboxylic acids and their derivatives chapter? Remember we did a whole section on acid chlorides, and I said acid chlorides are more reactive than, an ester and an amide and a carboxylic acid and an acid anhydride and all that stuff. Well, I said acid chlorides are really reactive, and you can react an acid chloride with two equivalents of an amine. So if you have one equivalent of this, you need to have two equivalents of the amine, right? 2 moles of the amine are required, because when you do the acylation, so this is called an acylation reaction. So we can put here, that's down here, acylation. You get HCl, and HCl is not a good thing to have in a reaction mixture. It's a strong acid, and so the second molecule of the amine, so RNH2 in this case, is going to combine with the HCl. So these two things come together, and you end up, did I put RNH3 when I meant NH2? There we go. So we end up getting the ammonium salt, okay, which is innocuous, okay? It's not a strong acid. So this is what, this is equivalent number 1, and then this is equivalent number 2. And I told you, what the pitfalls of that is, because it's like, if you worked really hard to make that amine, well, you lose half of it down the garbage can, so to speak. However, what we want to talk about here is that when you acylate the nitrogen, you can actually think of this acyl group as a protecting group. I'll just put here PG for protecting group. So how would you use an acyl group as a protecting group? We know that an acyl group can be removed either by hydrolysis in acid or in base. And if you don't remember that from the carboxylic acids chapter, I'll just review that with you quickly in just a second here. But check this out. Do you remember we talked about the bromination of phenol, for example? And we said it's so electron donating, it's so activating that it just brominates in all the ortho and para positions. Well, the same thing would occur with aniline. Okay, if you take aniline and you just treat it with bromine, okay, you just put it in some bromine, you're going to end up with bromines at both ortho positions and the para positions. So we call that polybromination. In fact, monobromination, where you just add one bromine, is really difficult to do. And you might say, well, hold on, why couldn't you just use, 1 mole of this and 1 mole of this, and then you'd only get monobromination? The answer is, yeah, you can, but you still end up with a mixture of monobromination at this position and then monobromination at this position. And you probably end up with dibromination and tribromination as well. So it's not a great reaction, pretty much useless, okay? So if you want to know, like, how could I do monobromination? Well, you can add an acyl group to the nitrogen, because then you take it from being an amine to an amide. And what do we know about an amide is that this is a strongly activating group, right? You put here strong activator. Okay, so this thing activates like crazy towards bromination, but this is going to be a moderate activator. Not nearly as strong. And so what's cool is if you treat the N-acetyl aniline with bromine, you just end up with the bromine going in the para position, and then you can hydrolyze the amide. You hydrolyze this bond either in base or in acid, either one. It says here the disadvantage, what's kind of crummy, and we talked about this during the amides portion of that chapter, is that the hydrolysis of an amide in acid or base is pretty rough. You know, it does require harsh conditions, but sometimes you just got to do what you got to do. Now, one thing I feel like the book is a little remiss on, and I always look over the book before I come to class, you know, I am your instructor, is that this is the hydrolysis step. So hydrolysis, okay? Yes, you can hydrolyze just using base. That's totally a thing. You can hydrolyze this bond in base. However, you can also hydrolyze it in acid. You can hydrolyze that in acid, but they make it look like it's a one-step thing to hydrolyze it in acid. That's not true, because then you'd end up with the aniline. Okay, so you know, to hydrolyze it in acid, first step is acid, and then in the second step, you treat it with, you know, a really dilute solution of sodium hydroxide to remove this proton and regenerate the aniline. Okay, so two steps for the hydrolysis in acid. And if you're wondering, well, which one's better, that would totally depend on the situation, and you know, you would have to make a decision on that. I've taught the class long enough to know that most of my students like the conditions that are less steps, and there's no problem with that. But either way, you need to know how to hydrolyze an amide. So other little things that we want to know, or that we have to remember, is that, and this is something that I mentioned way back in the electrophilic aromatic substitution section. We talked about how you can't do Friedel-Crafts on an aniline derivative. You can't just take an aniline like this here and then just try to do, I don't know, treat it with, you know, I'll treat it with methyl chloride and aluminum chloride. It doesn't work. You get no reaction. And the reason why is this is such a good a Lewis base, and aluminum chloride is a Lewis acid. So you end up making this complex, and now you've got something that's ring deactivating. So if you try to do a Friedel-Crafts on aniline, it just doesn't work. Okay, that's all you really need to remember at the end of the day. I'm not going to ask you, like, please write me an essay on why, you know, a Friedel-Crafts doesn't work on aniline. Number one, you just need to know that it doesn't. But number two, the reason why is because it reacts with the aluminum chloride, right? This is a Lewis acid. This is a Lewis base, electron donor, electron acceptor. And once you form this complex, it's deactivating the ring so much that you don't get anything happening. So you can imagine where I'm going with this. There must be a way to mitigate this. And the answer is yes, and it must be acylation, because it's in this section, and you'd be 100% correct in assuming that what we do is we add our acyl group. Okay, once you add an acyl group, you can do a Friedel-Crafts, right? Remember that the pair of electrons on the nitrogen of the amide, now they're delocalized. You could draw the resonance structure. There's no need to, but we know those electrons are not nearly as basic as they were, since they're participating in resonance with the carbonyl. The nitrogen is actually sp2 hybridized, and therefore, once you treat, or if you treat the N-acyl compound with, you know, Friedel-Crafts conditions, it's going to work. Okay, there's going to be no complex formed between an amide and a Lewis acid. So it's kind of a cool thing. And remember, just like the bromination, we only get the installation of the methyl group in the para position. I didn't mention it previously, but the reason why, you can imagine, is because you have free rotation around this carbon-nitrogen bond here. Since you have free rotation, it blocks the ortho positions, and so the alkyl group is going to go at the para position. Again, to hydrolyze the amide, you can either use base, or you can use first water followed by sodium hydroxide. Okay, either one is perfectly reasonable. There's nothing wrong with either of them. So this is kind of like using an acyl group like a protecting group. Okay, I would say that here you could actually call this a protecting group. It's not a blocking group. It's not blocking a position. What's it doing? It's protecting the amine from being, you know, from reacting with Lewis acid. So I would call it a protecting group. I don't think there's anything wrong with that. With all that in mind, you can see this is a long question, this one here. Let's just go through it together. It says, if you take aniline and you treat it with a mixture of nitric acid and sulfuric acid, the expected nitration product, which is para-nitroaniline, is obtained in a poor yield. Okay. Instead, the major product is nitroaniline. Apparently, the amino group is protonated under these acidic conditions, and the resulting ammonium group is a meta-director rather than an ortho-para-director. Propose a plausible method for converting aniline into para-nitroaniline. So all they're saying in the first part, let me just, if you're not following me 100% here, let me just show you what they're saying in the fine print section. Okay, so this is it. They say you take aniline, okay, and then you treat it with nitric acid and sulfuric acid, which we know are the conditions for nitration, adding a nitro group. And they say, well, this is an ortho-para-director, so shouldn't you end up getting this? Like, shouldn't you get just, put a nitro group down here? But in fact, you don't get this. Okay, this isn't what happens. Why? It's because since you're in a strong acid, what you actually end up making is this. You make the anilinium ion, and this is a meta-director. And so once it reacts with the nitronium ion, you end up with the nitro group meta. Okay, so it's going to be meta to this. So yeah, that's what you end up with. All right. So what they're saying is there a way you could make this compound? Is there some kind of way that you could do that would be plausible? Well, the reason it doesn't work is because this thing becomes protonated under strongly acidic conditions. So could we protect it? And the answer is yeah, we can protect it. How do we do it? We use acylation. I'm going to use my red pen here. So let's see. What we're going to do is we're going to take the aniline molecule and we're going to treat it with acetyl chloride or acetyl chloride, depending on who you ask, depending on it's like potato, okay? Tomato. Okay, so we add our acyl group, which is, again, a protecting group. And now, if we put this thing in strong acid, since the nitrogen of an amide isn't a strong base, it's not going to react with the acid. So we end up just taking this and treating it with nitric acid, HNO3 and H2SO4. And we end up installing our nitro group in the right place. So just bear with me here. Okay, that deleted everything, so I'll start over. So we start with this, and we acylate it first. This, so we install the acyl group. Now we can do the nitration, so nitric acid and sulfuric acid. And that puts our nitro group right where we want it, which is in the para position. And now you can hydrolyze it in acid and base. In acid, it's 2 steps. In base, it's only 1. So I'm just going to put sodium hydroxide, and that's good enough. And there you have it, my friends, a pretty neat synthesis of para-nitroaniline. And it works. Okay. It's nice to have a reaction that works. And again, you can think of this acetyl group as being a protecting group. This is a protecting group. It's preventing the nitrogen from reacting with the nitric acid, getting protonated and everything. All right, so there you go. Pretty neat synthesis. Give me a thumbs up if you follow me on that one. Is everybody with me on that one, or are there any questions about that one? Just the rationale. What they're really doing with this one is kind of explaining the rationale of why, one way doesn't work. And really, this question is nothing more than practicing acylation and explaining why it's a good thing. This is why you need to know acylation. Let's try another one. It says, starting with nitrobenzene and any other reagents of your choice, outline a synthesis of para-chloroaniline. So the thing is, if you were to take aniline, let me just draw some aniline here. And if you were to just treat this with chlorine, remember that the amino is a strongly activating group, and that's just going to chlorinate the heck out of this thing, and you're going to end up with this compound 2,4,6-trichloroaniline, which is not what you want. So you're going to end up with one here, here, and here, and that's not what you want. Okay, so is there a way we can just put a chlorine in the para position. And we know that you can do that if it's acylated, right? Because then it's going to mitigate the reactivity. It's not as reactive. You get that big old acyl group in the way. So let's write our conditions. First thing we need is aniline. So we'll scribble that down. The next thing we need is acetyl chloride or acetyl chloride. So that installs our acyl group. And the nitrogen, like that.
I'm sorry to interrupt, but
yeah, go ahead.
Aren't we supposed to be starting with nitrobenzene?
Oh yeah, with nitrobenzene. Okay, so I guess we have to reduce it first. So let's go. Thanks for pointing that out, Lindsay. That adds an extra step, doesn't it? The reduction step. Let's just boogie this thing over here. And we'll start with nitrobenzene. So I'm sure you all remember the conditions for the reduction of the nitro group. What did we say? We had a whole holy host of ways of doing it. There's iron, there's zinc, and HCl. Let's just use zinc and HCl. So we'll choose zinc and HCl. And then, of course, you have to treat that with sodium hydroxide. There we go. So now we've made aniline from nitrobenzene. Then we did the acylation. So now the reactivity is mitigated. So now this is not nearly as reactive. And now if we treat it with chlorine, Cl2, we're going to put that chlorine in the para position. Go. That. Go. And then we just knock that protecting group right the heck off of there. Let's just use some sodium hydroxide. If you wanted to use the two-step method, acid then base, that works too. Nothing wrong with that. And there we go. Pretty cool. What do you think? Does everybody think they could figure that one out on a quiz? Let's say you're staring at a quiz and it says, you know, which one of these would be an acceptable way to synthesize this molecule? All right, good. Yeah. Another one. So let's see. Hey, do you guys remember, and I know you do you remember in Organic Chemistry 1, I spent all kinds of time going over Hoffman and Zaitsev elimination, right? Like, let's say you had, I don't know, let's say you had, 2-bromo-butane, and then if you treated this with sodium methoxide, so NaOET, then you'd mostly get trans-2-butene. But if you treated it with a big old hindered base, like potassium T-butoxide, let's go over this side, potassium T-butoxide, that you would make this compound. And so I gave these names. I called this one the Hoffman product. There we go. And then the Zaitsev product. Does everybody remember that? The terms Hoffman and Zaitsev? The Hoffman just really means the less substituted alkene. It's nothing more than that. Well, I know we spent some time on that in Organic Chemistry 1, and I know I've brought it up in this class as well, but now you're going to see where it actually came from. The initial Hoffman elimination, just Hoffman always refers to the less substituted alkene, really, but the original Hoffman elimination actually used an amine to do the elimination. It wasn't a bromine, so I'm going to show it to you right now. We looked at all kinds of eliminations with alcohols, right? Normally you would take this and, I don't know, convert it into a tosylate, using tosyl chloride and pyridine, and then you'd end up with this, and then you treat it with a base, right? And then you could make propylene. However, now we're going to talk about the Hoffman elimination. Obviously, there's no regioisomers here, but the Hoffman elimination actually uses an amine. Do you guys remember?
Professor, we can't hear you.